Thank you very much, Ken, for a very interesting presentation, and we'll get back to you just after the next speaker, who is John Cullen from Dalhousie University, who's the Killam Chair of Ocean Sciences, and who is quite well known at ASLO, I think, from all his many publications and well-cited studies of many aspects concerning phytoplankton, such as environmental conditions, nutrient supply, UV radiation. John is also a fellow of the Oceanography Society. Notably, he'll be speaking on iron fertilization, but he's really been looking at this for quite some time. He was the co-organizer with Penny Chisholm of the first iron symposium when it was really a hot topic back in 1991. It still is. It seems to be a controversial topic. But I attended that meeting, and it was a seminal meeting, I think, for a lot of people, modelers as well as experimental data experts. And a lot of good papers came out of just that one symposium for the Limnology and Oceanography Society. He's also co-convened many different international meetings on a vast array of subjects such as HABs, as well as observational systems. And without any further ado, I'd like to give the floor to John.
Thanks very much. Good, we have the screen. Yeah, this has been going on for a long time, 20 years, and many times over the 20 years I've heard arguments that led me to believe, well, that wraps it up, we're done with this. And Ken's talk was so good, I would say, well, that's just so clear, we can move on. But experience has shown that no matter how clear arguments are, other things come up. So I'd like to go very quickly through a lot of material and leave some things out, but I'll start with just to reveal to you any potential conflicts of interest. I have no support from organizations opposed to ocean fertilization. I have no support or agreements with organizations that are proposing commercial fertilization. I do have an affiliation with a commercial organization trying to reduce carbon dioxide emissions, and that is Solana, and we're trying to pursue algae for biofuels and protein, and I've been involved in that for about 2 years. And I think it's useful just to reveal these things when one talks about them. So let's go back 20 years. It's for a lot of my colleagues, we've lived with this much of our careers, and for many of you, you were little kids. But in 1988, this was big news, let me tell you. John Martin came out with the paper and his colleagues that spawned the iron hypothesis, looking at iron and its role in ocean productivity. And this was a big splash in 1988. And John Martin, who was just quite a guy, came out with his quote, "Give me half a tanker of iron and I'll give you the next ice age." And this was his way of really driving home the importance that he felt could be placed on iron in climate ocean productivity. And let's be clear about what's going on and what the objective was and what the notion was, is if iron did limit nutrient utilization in the ocean, by adding it, it would encourage or shift this balance in the ocean of nutrients in the surface layer. The result of promoting production in the surface layer of the ocean is really to shift organic matter to the deep ocean, where it will decompose. So the big deal is organic matter sinks and it decomposes in the deep sea. Now, it was recognized very clearly at the time, and global warming was recognized as an issue, and very quickly the National Research Council Board on Biology in the U.S. convened a meeting with some prominent oceanographers. This was in 1989, and they came across with findings and recommendations that are actually not very far off what people are still talking about. There's all sorts of variation here, what the finding was that was conceptually feasible to do this, and we needed experiments. The big departure here was before peer review, their estimate of the cost was just a bit higher than what it turned out to be when it was done later on. What was strange to some of us was that we knew about this proposition, but it wasn't publicly available, and scientists were very agitated in the early part of 1990, but there was nothing anyone could do about it because it wasn't in the public domain. And strangely enough, this became prominent when it was published, not in Science or Nature, but in the Washington Post on Sunday, May 20th, 1990, and plastered across newspapers around the world that the greenhouse effect could be stopped for a few $100 million. And of course, there were also plenty of articles about the dangers inherent in trying to do this manipulation of the ocean. The American Society, well, we still had the name, the American Society of Limnology and Oceanography, and funding agencies responded very quickly and instituted this Iron Symposium in 1991. There was an open call for participation. It was really an amazing convocation. There were great talks, great discussions, and I'll tell you right now, in the final session on the last day, the issues that were brought up, the discussions, the questions, the arguments, they're the same arguments we have today. And there was a consensus resolution, and I've got to go through a lot of material. I won't read it to you, but you can pick all this up, and you may want to look at the 1991 symposium issue that's all available. The consensus resolution was research yes, geoengineering no. 1991. A really amazing and important outcome of the symposium was, I think, it endorsed the idea of pursuing research, and there is no question that the research that ensued has changed our idea of how the ocean works. It's been very, very successful. It's been published all over in the scientific literature. And one thing I think is useful to recognize is the details of this scientific research is virtually inaccessible to the general public because it's technically beyond what they can handle. And it's certainly beyond what the media is able to report in the way they have to talk. Now, it didn't take very long at all for commercial interest to be piqued, and claims for patents were filed, and in the mid-1990s, patents were issued, and one of the more interesting ones was for Michael Markles, who got a patent for fertilizing the ocean with iron chelate, and also that patent included possibly putting other nutrients, microorganisms, and even fish in surface layers of the ocean. Now, there's a recurring theme with this patent application, and they had a company, and the company advertised on the web, had all sorts of promotional materials. One thing that was very important was the unrecognized potential for side effects. And at this time, the proposal was to fertilize waters of the Marshall Islands in the South Pacific. And one thing that wasn't recognized at all was successful fertilization would change water transparency. And this graph here shows the relationship between coral cover and light penetration in the water. And there is little or no doubt that fertilizing these waters would have profound ecological effects by changing light penetration and influencing the corals. So not seeing the side effects was something that's been a recurring theme over a very long amount of time. Along the way, this is 2001, objections were raised. They were raised on and off here and there. This was in Science Magazine with Penny Chisholm, Paul Falkowski, and myself. And that article was rebutted by Ken Johnson and Dave Carl, and it was a good exchange. If you're interested, you can download that. But I think it's also safe to say that even though it's mentioned here and there, that this exchange was fairly well inaccessible to the general public at the level that it's really broadly seen. So the issue is already over 10 years old. There's been patents filed. There's all this commercial interest. Penny Chisholm and I had many conversations. Has this thing finally died out? And it hadn't died out. It just kept petering along and sometimes going up and sometimes going down. So we asked, what was the state of maritime law 10, 15 years after the idea came up? And up until 2006, it's safe to say, jurisdiction was unclear. There was no obvious recognition of the problem in the policy or management realm. There were definitely no strong lines of communications with oceanographers. And when I presented this at a meeting of the Law of the Sea group, Elizabeth Mann-Borghese, who was one of the founders of the Law of the Sea and just a wonderful protector of the ocean who's not with us anymore, assessed this as a policy vacuum. So that's pretty much where we stood in the early part of this decade. But during that time, there was quite an acceleration of promotion of commercial activity, and the most prominent group doing this was Planktos. And as you can see on this slide, some of you are very familiar with this, some are not, but there was a very vigorous promotion of ocean fertilization to stop the greenhouse effect, save the earth, and also to get rich. This came to a head in 2007 when Planktos announced a major program of iron fertilization, their so-called voyage of recovery. And by that time, they actually did have a ship, and they were ready to go out to sea. And this really raised the profile of ocean fertilization, galvanized the non-governmental organizations, and also some governments notified the International Maritime Organization, and things really got moving about that time in 2007. And the IMO did respond, so after 20 years, ocean fertilization was finally gaining recognition in ocean policy, and essentially what they called for was an environmental impact assessment of any further ocean fertilization activities. So 2007 was a big year because the scene was changing, and as Planktos was sinking, Climos was rising. And Climos was dramatically different in some ways from Planktos, and they had a highly reputable scientific advisory board. They had a code of conduct for ocean fertilization. They had a strong commitment to science-based policy, but importantly, they had a commercial model, and that is this activity would be funded and would be directed towards obtaining carbon offsets, and Ken described what that was about. And let's remember, the justification, the motivation, the reason why this has been promoted for 20 years, the reason why is that for climate mitigation. And climate mitigation means changing the trajectory of atmospheric CO2 by enough to make a difference. And that means mitigate climate change by moving a large amount of organic matter to the deep sea. This is quite critical. This wasn't bits and pieces. And a commonly mentioned target is called a wedge, and this is from this well-known paper, or should be well-known if you don't check it out. Pakula and Sokolo, and I pronounce their names wrong, right, Ken? I don't know. Stabilization wedges, but the notion is several technological we have to do as much as we can to reduce CO2 emissions, and if we could find 6, 7, 8, 10 activities that took 1 gigaton carbon per year each, this could go a very long way towards stabilizing CO2 emissions, so we can figure out what more we can do to help with the problem. So let's just remember the commonly mentioned target is a gigaton carbon per year, and in quantitative terms that is a lot. Now, later in 2007, there was a symposium held at Woods Hole, or workshop held at Woods Hole Oceanographic. I think 90 or 100 people were there, and out of that came a policy forum statement in which the scientists offered support for ocean fertilization, reducing the uncertainty surrounding ocean fertilization, and they certainly recognized these uncertainties, and in this article pointed out the need for more research to clarify these uncertainties. Also, recently, a special issue of marine, or a thematic section of Marine Ecology Progress Series was published. I'd encourage any of you interested to check that out. It is open access, so you can get them all for free. When we talk about science and policy and ocean fertilization, we can take a little diversion here, digression, and talk about a related proposal for which there's not a great deal of, or we do have scientific input, and that's a proposal that's been around for well over 10 years of pumping nitrogen into the ocean, originally ammonia, but now the proposal is for pumping urea into the ocean, and this is from Ocean Nourishment. And this is a lot of scientists recognize this is a lot more problematic than ocean iron fertilization. And if there's anything that I can recognize recently that is close to scientific certainty, it's this article signed or with over 50 authors stating that ocean urea fertilization for carbon credits poses high risks. So we would think when we talk about scientific guidance and policy that some issues would be put to rest, but a recent news release says the issue is still being pursued by those who are promoting it. So I think this gets to the theme that when Ken made some comments here that I would think made so much sense. You say, okay, that settles it. Let's move on. Well, that settles it. Let's move on. Now, there's important questions about ocean iron fertilization, and Philip Boyd and I have an article in the special issue, and also you can see the slides in much more detail on the Woods Hole site. You can see all the videos from the Woods Hole symposium on the Woods Hole site there. Just search on something reasonable like ocean fertilization Woods Hole. And the question we were asking, which is completely consonant with what was said in the science policy article, is can ocean iron fertilization be demonstrated to have acceptable, predictable, and verifiable environmental impacts? Acceptable, predictable, and verifiable. The notion of carbon offsets depends on this. The notion of manipulating the ocean depends on this. If this is going to be pursued as an option, we have to be able to predict what the effects are, and we have to verify those predictions. What is the goal of ocean fertilization? Everyone who has proposed ocean fertilization has said and justified it on the same basis. The goal is modification of the global environment. The goal is to reduce atmospheric CO2 below what it would be to a significant amount. That is enough to make a difference. That is modification of the global environment. To do that, the ocean has to be modified. The carbon has to be moved down. We talked about the gigaton. That means there are intended consequences. These are not side effects. Intended consequences of altering the ocean in this way include increased deep ocean concentrations of CO2, nitrogen, and phosphorus. Of course, that's the whole intention, move the CO2 down, and we all know from Redfield that means nitrogen and phosphorus as well. Concurrent with that, because of decomposition, it leads to decreased deep ocean concentrations of oxygen and also increased acidity. And also, because the nutrients are being stripped from the surface layer, it leads to decreased surface layer concentrations of macronutrients, but also altered ratios of nitrogen, phosphorus, and silica. And those of you talking about ecological stoichiometry know there are implications there. So what is the objective of ocean iron fertilization for climate mitigation? The objective is fundamental alteration of ecosystems and biogeochemical cycles on basin to ocean scales. That's the objective. Let's talk about some of the intended effects very quickly. One, an increased deep ocean inventory of nitrogen. Okay, carbon's going down, nitrogen is going down as well. That means acceleration of the nitrogen cycle. And a lot of this will be done in mid-depth waters, not really deep, because the organic matter is remineralized on the way down. And from the nitrogen cycle, as pointed out by Jed Furman and Doug Capone in the paper from the Iron Symposium, we have to look at secondary effects, which would include altered emissions of nitrous oxide, which has 300 times the greenhouse gas potential as carbon dioxide. This would have to be quantified, and this would have to be quantified over a time scale of 100 years And arguably, that cannot be done with acceptable accuracy, because this will be a cumulative process that happens remotely from where the individual fertilization events are. And as we argue in our article in MEPS, assessing the proximate effects by doing individual experiments and measuring nitrous oxide alterations is not enough to estimate what will happen on a 100-year time scale. And that nitrous oxide could, in principle, cancel out the greenhouse benefit of the ocean iron fertilization, and this has to be quantified and verified. Very difficult to do. There is another intended effect of ocean fertilization: decreased oxygen concentrations in the deep ocean, and not only in the deep ocean. Remember the important notion that only part of the carbon is going to go to the ocean that's deep enough to be removed from the atmosphere for 100 years. That means the rest is remineralized in waters that will come in contact with the atmosphere in less than 100 years. In fact, there's a very good chance the majority of the organic matter that's mobilized by ocean iron fertilization will be remineralized in waters that will come in contact with the atmosphere sooner. And those kind of waters are the kinds of waters that feed upwelling systems. For example, coastal upwelling systems such as that off Oregon that recently was subjected to rather catastrophic anoxia. So what happened off Oregon was there were waters with anomalously low oxygen and higher nitrogen content impinged, has nothing to do with ocean fertilization, had dramatic ecological effects. What happens if this occurs? Oh, one thing we can say with enriched nutrients and decreased oxygen in mid-waters, that the extent and duration of anoxic events will be increased, but we cannot say by how much. We cannot say by how much. But 10 years after ocean fertilization, there's an anoxic event. Is it going to be possible to say who or what is to blame? Is it climate change? Is it ocean fertilization? Is it climate change, ocean fertilization? We've seen this finger pointing on other issues in the past. This is something that will be very problematic, I think, in trying to understand what's happening if ocean fertilization is pursued. Let's talk a little bit about unexpected and unwanted effects, because I think that's what a lot of people are really worried about. You know, can we really predict what's going on? Well, there's a cane toad. And I think some of you know what I'm trying to represent here is the human race has a very long history of trying to do good things when ecological situations are going bad. The cane toad is one of many examples of ecological manipulations that didn't work out the way they were intended. So let's ask about the ocean. People are considering ecological manipulations on a grand scale. Can we really predict complex ecological responses to such manipulations? An example that I like to consider is the phosphorus additions to the Eastern Mediterranean Ocean, in which this wonderful experiment was conducted and phosphorus was added, and the chlorophyll concentration went down. And read the paper, it took some time to explain what went on and come up with reasonable hypotheses. But do we want to deal with ocean fertilization and find out that what really happened was explicable only in retrospect? On the basis of this argument, which I've abbreviated quite a bit, Phil and I proposed in the paper in MEPS that until the side effects of widespread ocean iron fertilization can be shown to be verifiable, and there is good reason to believe that they cannot, ocean iron fertilization should not be considered a viable technology for climate mitigation. So that was our argument. Hey, sounded pretty good to me, let's go home. No. There are very reasonable counter-arguments that have been made, and this quote from Andy Watson, that's in the Oceanus magazine special issue from the Woods Hole Symposium, is representative of a view held by many other people. And the quote is, "This is an incremental thing, and if you see things going wrong, then you can roll back." And I'd like to examine that argument. It's an incremental thing. This gets to the tragedy of the commons argument that Penny Chisholm and Paul Falkowski and I made in Science. You know, we'll just move along slowly. I'd like to give you an example here very quickly about ocean pumping. A lot of you may not know about it. A company named That Motion is interested in this. It was featured in the Discovery Channel. The Hungry Ocean. Dave Carl and Ricardo Letelier were on the TV and also wrote a paper about it in MEPS. And in the clips, which you can download, when we talk about incremental implementation, here's a quote from Brian von Hertzen. And he said, "This is really exciting for me because once we can prove that the technology works, we can scale it to millions of pumps." Millions of pumps. And I will move on. If you start to see that it's going wrong, you can roll back. This is an argument that's been given to me over and over and over again. We can do this, and if we see it's going wrong, we can stop. I already told you, and I said more clearly in the paper, we may not be able to see nitrous oxide reversing our effects. So for one, we may not see it going wrong. But let's consider, if we do see something wrong, we can roll it back. 1992, we saw something going wrong with the northern cod. We saw it in 1989. Other people saw it before. But it was clear something was going wrong. Canada imposed a moratorium on fishing, 1992. The cod did not come back. Now, I think three central questions have to be answered if ocean iron fertilization is to be considered as an option for climate mitigation. One, what are the effects of large-scale ocean fertilization? Without a doubt, fundamental alterations of marine ecosystems and biogeochemical cycles. Second question, can they be quantified with acceptable accuracy? I would argue no, but let's leave it a question mark. Third, can negative outcomes be attributed to individual applications, and can they be remediated? I'll leave that as a question mark, but I'll add, the burden of proof is on the proponents. The burden of proof is not on the anti-offset crusaders. I spent a lot of time trying to figure out how to wrap up this talk. I've given a lot of talks over 20 years. There's a lot of young students here. There's people with different views. There's a lot of scientific issues. There's a lot of egos. This is not about me. This is not about any one individual. This is not about a paper in this journal or that journal. This is what it's about. And I encourage all of you to think about it in that way. Thank you.